Module 23 Simple Linear Regression, Section 2 Simple Linear Regression. Assumptions. So before doing a regression test, there are a set of assumptions, 6 assumptions that have to be fulfilled. So if any of these assumptions are violated, then the conclusions arriving from simple linear regression is faulty. What are these assumptions? 1. Linear relationship model, whatever the model that we are going to generate is only suitable for the linear relationship. So if your x and y are not linearly related, or the variability is not linear, then simple linear regression is not appropriate. So if you have a curvilinear relationship or non-linear relationship, then you will have to go for appropriate non-linear regression test, not the simple linear regression. Scatter of the data around the line is Gaussian. So the residuals, that means the difference, some points will be on the top, some will be on the bottom if you standardize. So the scatter is following the Gaussian distribution, that is a normal distribution. That is another assumption for the simple linear regression. So as you know, the linear regression is a parametric method. It depends upon the parameters as well as the frequency distribution of the population. So here the scatter around the best fit line should follow the Gaussian distribution. Variability is same along the line. So if the line as a value in x-axis increases, if you go from bottom to the top or one side of the line to another side of the line, if the scatter increases proportionally, well, that is the case in many of the biological data. So in that case, simple linear regression need to be corrected. So if you use a standard simple linear regression model, then the conclusions are not valid. So data points or residuals are independent. So each of these measurements have to be independent. So if you are doing a dependent measurements like twins or left versus right eye, then conclusions are not valid. X and Y values are not intertwined. That means that if you are using X value to calculate the Y or vice versa, then you cannot perform a linear regression. X values are non-precisely, those are controls. You are not measuring it, you are deciding these x values. So only y values are measured for the linear regression model. See, this is the difference between regression and correlation. In the case of correlation, both the values you are measuring, but in the case of regression, only y values you are measuring. What are the hypotheses in simple linear regression? The null hypothesis is that the slope of the best fit regression line is 0. Line is horizontal and our model do not fit the data well. That is a null hypothesis, while alternative hypothesis is that the slope of best fit line is not horizontal. The line is non-zero. So that is, it's not horizontal and our model fits the data very well. That is the alternative hypothesis. So look at this data here. You can there are a lot of points. Then you make one best fit line, but unfortunately, this is not a good idea at all. But we will have to look at the kind of scatter or the kind of XY, the dot plot. So it is not a linear way of scatter. So the trying to fit all these points through a linear equation makes no sense. So that is the first step before doing the linear, the simple linear regression. Make sure that linear model fits your data very well. So once you do this regression, which is very simple in most of the statistical packages as well as so many online calculators as well, and Excel and GraphPad Prism can do the work excellently. You will get a table of this regression summary statistics, of which perhaps the most important values are the slope and intercept. So basically the regression, once you complete your regression, you are going to get 2 important parameters. So basically you are going to generate one line which is a linear line, that means the linear equation y equal to mx plus c. So of which m is the slope and c is the y-intercept. So these 2 values are most important. So in a way, calculating this linear regression is nothing but to find the values of these 2 important parameters m and c. So it also generates 95% confidence interval. That means the precision of the sample compared with the population. So comparing with the population, what is the sample as a good estimate or not? So that is what this 95% CI means. Linear regression fits a model to the data to determine the value of the slope and y-intercept that makes the best fit line of the data. You are generating the line or you are generating an equation. Both are same thing, same stuff if you put in two different kinds of perspectives. The best fit line is a straight line that comes closest to all the points in our dot plot. It finds the optimal linear equation that best predicts y given x or vice versa. So it's used for the prediction. So it's nothing but probability of data given the model or probability of D pipe that is given model, that is also known as likelihood. So regression is an example of a likelihood estimate. So basically, as you can see in this graphics, so the line, you can draw a number of linear equation models and out of which only one is perfect. So you are finding out which is the perfect linear model that fits the entire data very well. So that is least distant from all these data points. So that is exactly what this linear simple linear equation does. So vertical distances from the points from the regression lines are known as residuals. In that the graphics, residuals are highlighted with red lines. So residual is calculated by the y coordinate from the data minus y coordinate from the predicted line. So this difference is used for calculating the residual. Best fit linear regression line minimizes the sum of squares of the residual, so vertical distances of the values from the line. Simple linear regression, also known as least linear least squares. So it's not simply sum of the residuals, but it's sum of the squares of the residual. Why do you have to take squares? As you can see in this diagram, so there are only 2 points and the line is drawn in the center of this two thing. There is one way to draw. So from the line, that is a regression line, these 2 points are equidistant at 5 units. So let us say 5 centimeter across. So in this case, if had you calculated the sum of the distances or the residual sum, then 5 plus 5 is 10. In alternative scenario, you are drawing the line not right exactly in the center. It's biased towards the right. So in that case, one point is 9 centimeter while other point is only 1 centimeter. In this case also, if you calculate sum of the residual, that is 9 plus 1 is also equal to 10. So how will you decide which line is better, best fit? So usually the one which is least distant is the best fit. So in this case, if you simply take the sum of the residual, no, that is not a good way. Now let us see sum of the squares of the residual. In this case, the first case, it's 5 square plus 5 square. So that is 25 plus 25 is 50 is the one which is on the left side. And on the right side, it is 9 squared plus 1 square. 9 square is 81 plus 1 is 82. So given 82 and 50, so definitely 50 is the least one, so least distant, so most appropriate. So the line in the equidistant line model fits the data very well rather than non-equidistant model or the line. So 95% CI of any kind of regression line is always curved because they just have to accommodate multiple regression lines. So 95% of the time, the real population regression line fits inside your regression, this the 95% area. So that is why it is curved. So it doesn't mean that the relationship is non-linear. No, 95% is always curved because it needs to accommodate multiple regression lines. R squared is identical to the R square from the correlation. So both are exactly same value. R and R square are exactly same. So it is 59%. So what does that mean? 59% of all the variance in insulin sensitivity can be explained by the lipid content, and linear regression model, that is our equation. So by equation we can explain 59% of the variability of the insulin sensitivity by this model. And very low p-value indicates that the deviation from the null hypothesis of the slope is equal to 0, that is a horizontal line, is significant. So that is how to interpret this regression p-value. How can you perform this regression by hand? Basically it makes no sense to do this by hand because any computer can do this work within fraction of seconds. But if you are still curious, it's very simple. X, you plot the x and y. Then the next column will be x multiplied with y, the third column. The fourth column is x squared, while fifth column will be y squared. So if you have all these things, and the last row, let us make it summation. So sum of all these column, the 5 columns, individually you are putting as sum of x, sum of y, then sum of xy, sum of x square and sigma y square. So with all the 5 parameters, you can simply plug into this equation to calculate a and b. So I have provided the complete solution here. You can, if you are interested, you can give a try, and you are going to get these 2 values. One is a and one is b. Another is b. A is basically slope, while the b is intercept. So basically a is a y-intercept, while b is the slope. So if you have these 2 things, then you can plug into that equation to find exactly what the model is. So it is actually very simple to just plugging into these 5 values into this equation to come up with that. So in summary, linear regression fits model to the data to determine the value of slope and y-intercept that makes the best fit of the data. Best fit line is a straight line that comes closest to all the points in our dot plot. It finds an optimal linear equation that best predicts y from x. Best fit linear regression line minimizes the sum of the squares of the residuals, that is vertical distances of values from the line. Thanks for watching.